This is an example problem for a particle in a one-dimensional box. We're trying to find the wavelength of maximum absorption, and we're given an equation for that, 8 times m mass of an electron times a squared times c divided by Planck's constant h times n plus 1, where n is the number of pi electrons in the system. It's for octatetraene, and so that's 8 carbons. Let's see if I can get this right. 3, 4, 5, 6, 7, 8. Note that the shorthand way of doing this is like this. So every double bond is 2 lines, every single bond is a single line. There's a carbon at every kink in this sawtooth structure. Since carbon makes 4 bonds, if they're not explicitly listed, then there's a hydrogen there. We also are given some other information that the mass of an electron is 9.11 times 10 to the negative 31 kilograms. The speed of light, which is c, is 3.00 times 10 to the 8th meters per second. And Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. And a joule is a kilogram meter squared per second squared. So multiplying by a second gives me seconds instead of seconds squared. And I'm looking for the wavelength of maximum absorption. So now all I need to do is figure out what n is. So when I look, there's 4 double bonds. We also call these pi bonds. And since 2 electrons make up a bond, I have 8 what we call pi electrons. That's equal to n, so n plus 1 is equal to 9. So I've got this, I've got h, I know what 8 is, I know the mass of an electron, I know the speed of light. Now I need to find out what a is. And I forgot to write it down, but it was actually in the problem. We have carbon-carbon double bond distances and carbon-carbon single bond distances. The double bond distance is 134 picometers, and the single bond distance is 154 picometers. So now I can find A, which is the length of this conjugated molecule. Let's see, I have 3 single bonds and 4 double bonds. So 4 carbon-carbon double bonds is 536 picometers. I have to remind myself that pico means 10 to the negative 12. And for the single bonds, I have 462 picometers. And so my total here is 998 picometers. And so undoing the pico abbreviation, I have 998 times 10 raised to the power negative 12 meters. So now I have everything I need to calculate my wavelength of maximum absorption. That's equal to 8 times the mass of an electron, 9.11 times 10 to the negative 31 kilograms, times a squared, and that's 998 times 10 to the negative 12 meters squared. I'm going to put it down here since I'm running out of room, times 3.00 times 10 to the 8th meters per second. And I'm going to divide that by Planck's constant, 6.63 times 10 to the negative 34 kilogram meters squared divided by second, and divided by 9, which is n plus 1. I do have to make sure my units work. So seconds in the denominator here cancels these seconds. This kilogram cancels that. I have meters squared here, which cancel these. I am left with meters. That's great, because that's exactly what I want. So when I run this through my handy dandy calculator, remembering to square the value of A, I get 3.65 times 10 raised to the power negative 7 meters. I'm going to substitute in an abbreviation here. 10 to the minus 9 is nano. So I get 365 nanometers. And in reality, it's 273 nanometers. So this model of a one-dimensional particle in a box isn't perfect, but it sort of gets us in the right ballpark. Notice as A increases, the length increases, the number of pi electrons is going to increase, but A is squared and N is not. And so the longer the conjugated chain is going to get, the longer the wavelength of maximum absorption is going to be.